to be able to do such a statement, we need quite some data. So just to summarize, if you're talking about critical concentrations, we could think of how is a concentration determined if you look downstream in a river. So what is this concentration C? We usually take C for concentration. And of course, versus the input can be either point sources or diffuse sources. Then they will travel, so that's the transport part. And that can either be adaptive transport or dispersive transport. And there are processes, so that could be produced, it could be decayed or whatever. And that's all together gives you a certain critical concentration or a concentration at a certain downstream point. Just to, I probably have told this already in some previous courses, but still we have to get a certain starting level, and it's probably not all new, but I'll tell this anyway. The first thing we have to take into account is if you have a spill, how to estimate or how to start with a certain starting concentration. And for instance, we have a river with a flow rate Q and a concentration, background concentration of C1, and there is a spill or some loading factory or whatever, Q2 with concentration C2, and what will be the concentration C3. Obviously, for the water, you can just sum them up. If you have a flow rate of 1 cubic meter and the other is half cubic meter, then afterwards it will be 1.5 cubic meter of water. But you cannot just sum up the concentrations, because it's dependent on the ratio of the different flows. So then you make a load budget. So load is concentration times discharge, and these loads you can sum up. So the load at Q3, that's C3, Q3, C3, is you can just sum up the loads of 1 and 2. And with that in mind, you can calculate the starting concentration after the spill with this last equation. You could have thought it yourself, but I just want to give that here that we remember this again. Now we will look at derive a general equation for mass transport. And we usually start with this volume with 3 dimensions, dx, dy, dz. And there is a concentration in the volume, and there are flows in 3 directions. And we think of the balance of mass. So that means that the difference between in and output and the processes together determines how much is accumulated within this volume of water, for instance. And that can be either a negative or positive accumulation, so that it can be a loss, a sink, or it can be a source of production. Then if we look at 3 adjacent volumes with a transport, we could define the concentration and change in the middle volume by setting up different terms of the equation and taking into account that the cross-sectional area between 2 volumes is defined as dy dz, and then if you multiply with the flow velocity u in that direction and the concentrations in this part and that part and that part, and you combine that all together, you can set up the mass balance for this volume actually here. And if you rewrite that and integrate to very small dx, dy, dz, then you will have this final differential equation, partial differential equation, which says that the change in concentration is the three-dimensional flow in the x and y and z direction multiplied, so the gradients in these directions, Ez, multiplied with the flow velocities in the three directions.
Als je verandering hebt, als je bijvoorbeeld hoogwaardig tijdschrift minder wordt, in het gebiedje groter van tijdschrift ga je erbij.
Okay. There's a question about the processes, probably, process rates. And then you will have a time variable indeed in it, but I'll come to that later. This is just the conservative transport, this is the real transport. So the effective transport, that's the transport because the rivers flow and they take the substance with it, just to make it simple actually. And then the second type of transport is dispersion. And I know that some people already work with that, but just to explain it anyway shortly. Dispersion is the mixing of the substance usually in the longitudinal direction, because of that this plug of substance will not stay together but will be gradually dispersed in the two directions, because there are gradients in flow velocity. Near the bottom it's flowing less fast, and near the banks and in the middle it's flowing faster, so you get the spreading of the plug of your substance. And it could also be because of plants or rocks or whatever that creates turbulence. And actually it's also a kind of molecular diffusion, but that's on a very much lower scale actually than dispersion. And that will look like this, that you have an input here, and at some distance downstream you will see this type of profile, and more far downstream you see a more flattened profile, so wider but less high. That's what we call, that's the effect of dispersion. And this is usually described with Fick's law, where you have this dispersion flux is determined by the concentration gradient, so the difference in concentration over the distance, and then multiplied with a certain factor, the speed, which is the dispersion coefficient. And to give you some idea, some numbers, this dispersion coefficient is very system specific, and the people who did the Hubsel course last year, which are the soil water atmosphere students, they know because they try to measure this, and I will show you some results of that also. So this dispersion constant can really have different ranges, so it can be really high numbers using a large system, estuaries and large rivers, or small streams, they have a really much lower value. This is a picture that shows that this dispersion effect, or the response of loadings, can just be added together. You here it's indicated on this axis the different loads, and this is time axis, and there's different loadings, so it's not one loading but different loadings, and you see the red one, which is the sum of all the responses. And as you can see, the first loading, this was really a high one, and then there were three together, and you see them as two peaks in the response curve. So every loading has its own response curve, indicated in black here, but you will, if it's the same substance, you will find just a total response, and that can be this red line actually. And this is a measured field concentration in Hanover, just below a chemical factory. So now if we combine both advection and dispersion and we keep it to 1D, otherwise we have an X and a Y and a Z all together, and that will be really a long equation. I think it might be that in the manual it's the 3D version, but here I just show the 2D version, sorry, the 1D, which says that the change in concentration is an advection term, it's a dispersion term, and it's a processes term. Here the processes come into account, and that can be any time variable that you would have, and that's integrated here, depending on how what type of processes you're thinking of. Usually these are first order reactions, so it means that it's exponential decay or an exponential growth depending on the concentration of the substance itself. And I assume most of you know how to deal with these first order reactions and do calculations with it, but we will do this also in the tutorials. So this is the basic, this 1D advection dispersion equation we use to solve, and it's depending on the type of, let's say, pollution case or transport case that we want to solve it for. And this will be mostly done in theme 5, where we really look at different types of loading and different systems with or without dispersion, permanent load versus a pulse load, and that sort of stuff. And I will here just now go further on one specific case. That's the dispersion in running waters. And it means that you have a dynamic dispersive system where there's a loading of a chemical at one specific instantaneous moment. And if you integrate this, the previous equation, this advection dispersion equation, this is the solution if you have this type of system. I don't expect you to do this integration. I'm not able, if I can do it myself. So it's more that you know where it comes from and that you're able to apply the right solutions of this equation at the right type of problem. And that's what we're going to exercise. So this equation gives the response curve of such a loading, usually a spill of a certain substance. And then this could be a response curve if you have the distance on the x-axis. So if you were able to, let's say, if we take into account this loading in the Rhine, downstream of Leverkusen, of this Bayer factory, and we were able, let's say, here is Bayer on the left side, and on the right side is Holland with the border of the Netherlands, and we were able to sample every meter or every 1 kilometer and make such and that should be at the same time. So at one moment we have, let's say, 1,000 people with a probe or with a bucket taking a sample, and at the same moment we all together we shout now, and they all take a sample at the whole stretch, and we analyze for the mass. Then it would look like this. It would be symmetrical. So we have most of the substance is flowing together with flow velocity, and a bit of the substance is going faster and will already be here, and some part of the substance will go slower and will be more downstream. And now a question for the soil water atmosphere students. What if we put the time, if we just sit on one place and we measure in time how much substance is passing? Would we have the same graph or not? Or how would it look like? There's a no there. Or would it be, if you remember? You can't remember from 1 year ago? I think it was 1 year ago. See if I can use this nice board to. Okay, if you put t here instead of x, so now we sit in one place and we take samples every 10 minutes at the same spot, let's say 100 kilometers downstream the spill point, then you would probably measure something like this. See, I almost looks like I practiced this. It was a nice fluid line. So if we could work on this a bit further, but it's important to realize that if you look at a certain location and you look in time, then the first bit that will come is very rapid because it's really fast that it will come. And then, so there's a short time. So in that time, there was only little dispersion. But if you wait longer and longer, there's more and more dispersion will happen. So there's a long tail because here is a lot of dispersion, and here there was only little dispersion. So therefore, you get this asymmetrical pattern actually. And I've summarized this. So it's symmetrical if you have the x or the distance on the axis, and it's asymmetrical if you have time on that. It's a bit complicated to picture that, but it's an important aspect of this type of equation actually.
Is that influenced a lot by how the river flows? Like, for instance, you have laminar flow versus what's it called? Thank you. So, like, if rivers more wildly flow,
Yeah.
like, for example.
It's definitely the type of flow that determines this, because if you all this turbulence in the water will be reflected in the number of this E. So if this has a high number, then it's more spread out. So it means that the concentration will probably be lower because of the spreading. And if it's a really straight canal with a very little frictions, then the plug will stay more together, and then it will be much more peaky actually. So that's how it's expressed.
The wet cross-sectional area, is that at the points where the slow flooding happens, or the average over the entire canal?
Yeah, that's a very good question. This is actually only valid if you assume this cross-sectional area, for instance, and also the flow velocity as constant. And this makes it really complicated to do this type of simple, straightforward analytical solutions. So it's just to have a rough estimate actually.
I think the same goes for E, that has to be constant as well.
Has to be constant as well, and that's also not. Yes, good question. So this assumes sort of identical conditions over the whole stretch. So even if the people from Stichting Rijnwater had this formula, they didn't have this equation and all these different cross sections and so on. So I doubt whether they could tell something. So how to measure dispersion? There's some pictures. I see someone here who is, and perhaps some more. These were pictures of last year's course where the students tried to measure this dispersion constant. And I already told them next year we will go more in deep of the backgrounds, but here. So perhaps you can explain what was done, but you're here on the picture, so.
It's not me.
It's not you really? No?
Yeah, no.
You were there, definitely.
Yeah, I was there, but not on a picture.
Okay. Okay. So it looks a bit better. Okay. Now what we did here is we loaded some amount of salt, just sodium chloride, and we measured the electrical conductivity. That's directly related to the concentration of salt downstream the loading point, and we try to make this nice graph and do some calculations on that. So that's a way to do this. And so it was input of a tracer, and then you look at the downstream response curve, and you try to calculate with discrete measurements what will be the outcome. And there were two things that we then calculate. That's the average residence time of the substance. So that means what is average time that the substance takes to get from the spill point to where you are measuring. On average, because this is not fixed. As I said already, some molecules will go fast, some will go slow, but on average they will go at a certain speed. And secondly, you can measure actually the variance of the curve, which means how far is it spread out. That's calculated with these numbers, and we'll do this in the tutorials, and then the people of the solid atmosphere course are a bit in advance. But surprisingly, I never see that in the exam. So somehow they think lightly of that. So, no, we did that, we know how to do this, but on the exam, I get really strange answers. So I advise them to redo this. Just redo this and know how it works. So we will, for the rest who are really thinking, oh, what's this? We'll practice this in the tutorial. There's another thing that we should take into account is the total mass of the tracer that we put in. That can be calculated if we integrate all the concentrations that we measured and multiply with the flow rate. And that can be determined with the velocity and the cross-sectional area, assuming again, as was said, that it is sort of constant in our period. So, and then, if we combine the equations, then we could make two relations. One is the ratio between the residence time of the substance and the residence time of the water. And the ratio is the variance over the residence time of the water to the power of 2, actually. Combining these two equations, you will get this solution. These are fast steps, and as I said, if I want you to remember derivation of the equations, I will tell you, and so far you can do it just with the outcome, actually. And I think Bart also told you that it's an open book exam mostly, so there's a half or some part is a closed book, but then you have open book, you have everything with you. So just be sure that you select the right equation for the right problem. That's usually the main issue here. I was wondering if I forgot something to tell you here. Yeah. One nice thing of this rather complicated equation actually is that we can make one simplification, which is that in this point, just forget the red. I don't know how to skip it. Perhaps I can erase that. Perhaps that works. Yo, it works. So, where the top of the concentration profile, that is where that follows the water speed. So there's a spill, the water flows with a certain speed, and the plug of the substance will follow this water speed. So the bulk of the water of the substance will follow the water speed. Some will go faster, some will go slower, but the main part will follow the water. So it means that here the distance in this point is equal to the flow velocity and the time. So the water has traveled 10 hours with a certain speed and has done a certain amount of kilometers, and that is also where the peak is. So if we know, then we know in the peak of the graph, x equals the flow velocity times t, and if we fill in this here, then you will see a 0 appearing, and e to the power of 0, that's 1. So this whole exponential part will disappear, and then for the maximum concentration, we have a simpler equation. So to remember that, the first part of the equation describes the maximum concentration, and this exponential part, which is two-sided, will indicate the tail section. So now I'll go back to why I wanted to say that is that yeah, that's time, so I will just finish this quickly. That how we can use this is that if we have a certain loading of a spill, for instance, here's a factory, and due to some accident, 100 kilos of a certain substance or pesticide is loaded, so M is 100 kilos. There's a dispersion constant that we can assume in this part, and there's a cross-section of 200 square meters, and there's the distance of the industry to the beach of 10 kilometers under the flow velocity. And then the question is, could we already make a guess or a sort of estimate how much the concentration will be, the maximum concentration at the beach? And then we could use this simplified formula. See if I can write that here, because there's no blackboard here, but a whiteboard. So we said that C max is m over 2a times the square root of p times the dispersion constant times the time. And we could look at what we have here. So we have the m. Take care this is in kilo, and I mix up everything. So always you have to check the units. Yeah. So if you want to have grams, that would be 100,000 grams, but it's depending on what you would like to know for concentration. The dispersion constant, that's given. Cross-section area is given. But there is no time given when it will reach the beach. But obviously, the flow velocity is 5 kilometers per day, and the distance is 10 kilometers, so t is 2 days. So now we have everything to fill it in, and if you do it, please check how someone is calculating, see if it's right. And also, I just pointed here because this goes wrong always. Milligram per liter for concentration equals gram per cubic meter. What was the factor of tau? Do you think this is two things? One thing that you should really remember, but you, of course, you remember that, but it's important that you do this right. You have an answer?
Yes. 0.21 grams per cubic meter.
I think I have a different answer. This is my answer. But okay, you can redo it and see if you can find the same answer if you use this simplified equation. Okay. Questions on this first part? And I suggest we have a short break, maximum 10 minutes, and then we continue with the second one.
Ik wel. Ik vind het prima, maar tijdens de voorgang dat dat Thijs kunnen we.
So far, we discussed what was the previous lecture about. It was on diluted or dissolved substances, so substances, ions, so that completely dissolve in the water. But now we will look a bit on what particles do in water. And because they are not dissolved, but they float, or they sink, or they whatever, but they are in suspension, but they perform differently than dissolved substances. Did anyone take the course, what's it called, geophysical fluid mechanics? You did? 2, 3? Okay. And some parts, at least maybe recognizable for you, but we'll see. So we will mainly discuss two processes that particles do, which is settling, sedimentation or deposition, and resuspension. And why this is important for water quality is, of course, the whole light climate in the water is very much influenced by turbidity of the water, so how much suspended particles there are in the water system that will absorb or scatter the light. As you can see in the left upper picture, completely turbid, and you can expect that not so much animals and plants will grow in this type of water, let alone if it's polluted or not, but at least there's no light. And in the right picture you see clear water. But also, which is indicated on the picture down here, there's the dredging of canals, so removal of sediment, which is, especially in the Western countries, is very often polluted with substances because a lot of substances tend to attach to particles, organic particles or clay particles. So the transport of pollutants can, in this case, is very much related to the transport of particle itself. And there will be also in team 4, so the afternoon team of next week will also be discussing this type of absorption and desorption processes of chemicals. So, so of course, for the morphology, so how deep the water is or how shallow, buildup of sediments, for instance, is important to know. Settling and resuspension, the light climate already, I told you, absorption of pollutants, but also ecology is very much affected by the state of the sediment. So if we have a big particles in the form of grains for fishes to spawn, that's completely different from very black, fine organic material. And of course also the transparency is important for recreation, for their safety, to see what's underwater. So, so we will look at suspended solids. If it's in the water column, we call it suspended solids, and if it's on the bottom, we call it sediments. And there are two cores with different locations, and you can already see that they differ in the sense that here is a lot of sand, or there's coarse organic matter on top, and here it's really more fine, compact clay with organic material, so it can have any forms. And these are actually cores taken from shallow lakes in this neighborhood. Yeah, to make it a bit simple, we can distinguish and characterize sediments on the basis of the amount of organic and inorganic material. And one of the methods to measure that, that's the loss of ignition, that you just dry the sediment and then you burn all the organic material at over 500 degrees, and what is left is the loss of ignition, and that's actually that's the organic part is the loss due to this ignition, and so you can distinguish between organic and inorganic part. And there is the grain size that could also characterize a lot, so different classes of sand to clay, actually. So there's the two processes, settling and sedimentation and resuspension. And if the resuspension is lower than the sedimentation, then there is a net sedimentation and build-up of sediment. They can happen at the same moment. That's sometimes a bit not so straightforward to realize, but resuspension and settling can happen at the same moment. It's because of the different compositions and the different classes of grains that you could have. So first, if we look at the sedimentation flux, so that's the amount of particles that will settle on the bottom, and this is an aerial flux, so it's per square meter of sediment, for instance. So it's the unit is grams per square meter per certain time, and that can be seconds or days or hours, and it does not really a fixed time unit. It can be anything as long as if you in the calculations you use the right units. And this is determined by the settling velocity, so how fast the particles will go to the bottom, multiplied with the concentration of suspended solids in the water column. These two determine what is the total flux. And if you just also check the unit sometimes, and then you see it's meter per second multiplied with gram per cubic meter, and then you see that indeed the unit of this settling is gram per square meter per second. To determine in what way this settling influences the concentration in the water column, we have to look at this volume, for instance, a volume with V, with an area of A. There's a suspended solid concentration, there's a height of the water column, and there's a settling flux. And if we now calculate, if we assume this volume and a change in concentration in this volume is the settling rate multiplied with the total area. So this is the area of this volume, and this is the settling rate per square meter multiplied with this area gives you the total loss from the water column, which is a change in concentration times the volume that you have. So it's a mass balance over the volume. And then if we assume that the volume is equal to the area times the height, area times the height, that's the volume, and then you can derive this concentration change of suspended solids in the water column is minus the settling velocity divided by the height of the water column times the suspended solid concentration. And we could say this is a typical first order equation which has a change in concentration is dependent on the concentration itself times the first order removal rate in this case for suspended solids. This first order removal rate or production rate or decay rate, you always have the unit of per time, in this case per minute. So now just have a look at a case that we have a lake, and this has a volume of V. Sorry. And there is a suspended solid concentration, and there is a loss rate here, and an inflow and an outflow. And we make an assumption that this lake is completely mixed. So it means that it's completely mixed, that there's no concentration gradient in the lake itself. So the outflow concentration, obviously, is the same as the lake concentration. Of course, not the inflow concentration, that could be anything, but there's an inflow, mixing, and there's an outflow. So the outflow concentration is the same as the lake concentration. That's an assumption that we make. We could do that for well-mixed small lakes, for instance. And we have this loss rate, and this is first order loss rate. And as we saw in the previous slide, if it's settling, if the loss is just settling and not decay or whatever, just settling, we could say that this loss rate is the settling velocity divided by the height of the water column. So expressed in this first order equation. So now we can set up a mass balance which says that this is the change of the total amount in the lake. So it's the concentration change times the volume. So this is the change in grams in the whole lake because of inflow, outflow, and this settling process. And obviously, the inflow is the flow rate times the concentration, which gives you the total influx in grams per second or grams per any time unit. And we can look at the equilibrium concentration, so in steady state. And what's an equilibrium concentration? It means that at a certain point the concentration will not change anymore. So ESS dt is 0. And also we can assume that the volume of the lake is more or less the area times the height. And of course, if this is really the cross-sectional area, then it's not valid, because it's not everywhere the same depth. But if you have a wide, shallow lake, then you usually can do this. Only on the banks you have some small deviations of this assumption, but we usually can do it. So if we say that this is 0, then we could say, okay, what would be the concentration, SS, in case this becomes 0? And then you can just rewrite the whole equation. And I suggest, and we will, this is also one of the exercises that we will do tomorrow or Wednesday, I'm not sure. But to rewrite this to this equilibrium concentration. And it says here, so the final concentration in which there is equilibrium, so all what's coming in will settle or flow out, but the concentration in the lake will not change anymore. It's dependent on the inflow concentration, on the settling velocity, and the cross-sectional area over the flushing rate. So that's actually more the hydrology, so how much water is going in. We will, as I said, we will try to do some calculations. So this is one of the applications of this settling rate concentration formula actually. So what's actually determining settling? So what's the behavior of the suspended solids? The settling velocity, that's because the particles will settle because they have a larger, how do you say it? They weigh more than the water, specific mass actually. So they will settle, and you can calculate this with Stokes' law if we assume laminar flow, which is in water systems not uncommon. And so it says that the settling rate of a particle, so the velocity of settling, is dependent on the density of the solid and the difference to the density of the water, and some other units here, which is the viscosity of the water, some other units like the acceleration of gravity, but also the diameter of the particle, which is important. We're going to use this with a known settling velocity. We could calculate the diameter of the particle if we assume that we know the other things. That's also one of the exercises. You could measure sedimentation with what we call sediment traps, and I made a drawing of this. This is a sediment trap consisting of a tube, usually of PVC or some other material. It could also be iron, but that will not float that much. So, but it's open on the top, and it has a floater, usually of polystyrene foam, so it will stay upright. And if you want to keep it in place, you usually connect it to a stone or some other weight, and you put it on the sediment, and it will stand upright during some period of time. And the particle concentration here, some of the particles will settle in the tube. And because it's a very long tube, there will be no resuspension, because the waves and the wind cannot affect the bottom of this long tube. If you make it a bit long, then you don't have the problem. If you put a plate, you could also say, okay, you can put a plate here, a flat glass, something like that. But if it settles, it can easily be resuspended again, so you have to capture it somehow. So therefore you have this settling tube, sediment trap. And so there's no resuspension, so the settling rate, or the settling flux, will be the settling velocity times the concentration. We already saw this. So if you put it for a certain time, this time, with an opening A, and you can easily derive that the total mass that you will find at the bottom of this settling trap, the sedimentation trap, will be the, shouldn't touch this, Sorry for that. It's the total flux, but it's in gram per square meter per time. So you have to multiply with how much square meter is this opening, which is usually far less than 1 square meter, but you have to take that into account. So also multiply with the area and also how long you will last this experiment. It could be 1 week, it could be a day, but depending on what you expect from how much will settle. And then the total mass in grams will follow from this. And usually we do the other way around, so we put this, we let it hang for 1 week or whatever, then we take it out and we measure how much mass is settled in the tube. So we know, of course, and we take a sample of the water to determine the suspended solid concentration. So we know the suspended solid concentration. We can, of course, calculate the area. We know we did 1 week, 7 days, and we can measure how much mass we captured. So with that, we could calculate the average settling velocity of the particle. So that's one way to estimate the average settling velocity of the particles. That is a question.
Does this also work in flowing water? Because I can imagine the top of the tube causing some turbulence as well.
Yeah, yeah. Actually, it's even better working in flowing water, because then the water on top of this is mixed all the time. And if you do this in a lake which is hardly mixed, then the particles here will settle and they will not be refreshed, so there's not a constant settling. So you should, now I draw this here, like this is only very small part, but this should actually be at least 1 meter or something, otherwise this will not work. But especially because of the mixing, it's better to have it in flowing waters. I have a very short video to show you. Let's disclose. Okay. Again, let's try. Sorry for the Dutch, but this says that we will put up sediment traps in the small river the Dommel, which was a master student's project for a few years ago. And she made a model of the transport of sediment all over the river Dommel, depending on different rates of settling. There was some sound, but that doesn't matter. So now you see here the tube, and with the small and with a stone to keep it on the bottom. And usually you place a lot of them in a row, something like that. And here you see John Beyer. Some of you might know him. And it's placed on the bottom. Here it's not too deep. Sometimes it's quite deep. And you always make a rope, because then you can find them back. Otherwise, you really have to look where they are actually. And so they are. I'll stop here because the other is on light measurements, and that I will not continue. So this is to measure settling with the sediment trap. Okay, now we will discuss. There's a question.
Is there a rule of thumb of how high in the water from the bottom you should place such traps?
A rule of thumb at what depth you should place them.
Yeah.
Ideally, you should dig them into the sediment, and that it's leveled with the sediment. But then you have the whole water column. So it's already a bit of a flow, or let's say an artifact, that you have this height. So you only measure what's happening above the column. So you should put them as deep as possible.
But if you put them on the bottom, there's no resuspension. you
But
do
it-
expect resuspension if something is on the bottom, right?
Yeah, but how should that affect? If there's no resuspension, you think that would be, how would that affect our measurements? You just want to know the settling velocity. And there's just this tile that you put on. Okay, in this part there could be no settling, and of course you should do that very carefully, because if you stir up a lot of sediment very close to the tube, then you already make an error on that. So which questions about it? You were first.
If it's attached to a rope, and if you use a small rope to attach it to the plate as well,
Yeah.
does the tube sway at all?
Yeah, they do. But as we did this in the normal, and it was quite flowing 20-30 centimeters per second actually. But because of the foam, it stayed quite upright. That was surprisingly, yeah, it was okay.
But isn't it not wrong that you missed with such a lot of data? By the heaviest material is the lowest part of the
Yeah.
record. And then
No, yeah, but that's okay. So your question is does it? Don't you make a wrong measurement because it's only the lightest part that you take? Yeah. Now especially because of the flow, the water column is constantly mixed. So there's not really a gradient of particles in the water column. You would expect that because if they settle, but they are always mixed. But once they hit the bottom, they're out of the water column. But just above the sediment until the top of the water, it's always mixed. And then particles can escape by settling, but it usually is completely mixed. Okay, but it was a good question. So the opposite part of settling is resuspension. So it means that because of some drag force, particles can be lifted from the sediment into the water column. Usually if you have an increase in flow velocity or an increase in wind speed, for instance, in lakes, making these turbulences, then you could have resuspension. And you can all imagine how you have seen the small streams in the mountains. They are usually very clear, but once you have one rainstorm and the water speed increases, that they turn turbid immediately, usually completely gray or whatever, because of resuspension. And this happens when the force that is expressed or on the sediment is stronger than the strength of the bed itself. So it means that it takes some basic strength to get it in resuspension. And this bed strength is dependent on how compact the sediment is. If there are, for instance, benthic algae, so algae that grow on the sediment, are making a sort of cover which makes it more difficult to resuspend for particles, but also the grain size. You can imagine that very fine particles will resuspend much faster than the big stones, of course. And usually we express this force in a shear stress, expressed in Pascal, for instance. And once you have a shear stress which is exceeding a certain critical shear stress of the sediment, then you will get resuspension. And these forces, as I put here, could be due of water flow and wind, of course, but also fish can do that. A lot of fish can make some forces by just going over the sediment. And for the people who are sometimes sitting at the canals in Utrecht, for instance, where you have these nice bars, and once a ship passes, it's completely black immediately because of resuspension of all these boats, for instance. So that can also be the reason. And this drag force, So the shear stress can be calculated from different units. This the cc concentration, so that's the amount, so that's the roughness factor, the density of the fluid, and so on. But just for now, it's interesting to realize that this drag force is proportionate to the power of the flow velocity. So once you get a bit of flow velocity more, you immediately get a lot of more shear stress on the bottom. And for wind, you could look at this picture. These circles, they are called orbitals. They are circles where the water moves in contradicting directions, and they will fade out to the depth and becoming smaller and smaller. And there's also a rule of thumb that if the depth is larger than half of the wavelength, so that's the length of the one wave, then these orbitals will not reach the bottom, so this will not contribute to any resuspension on the bottom. But if it's really shallow and there's a lot of wind with high orbitals, then you will get an up and down movement finally on the bottom, which resuspends these particles if it's strong enough. Just to describe these resuspension fluxes, so we said that if it's the critical flow velocity is not exceeded, so the smaller than the critical one, the flow velocity, then nothing will happen. In theory, of course. And if it's larger, then there is a certain increase of resuspension flux depending on the difference between the flow velocity and the critical one. And there are a few ways to describe how this works, but this is the concept of Lam and Jacquet, and it looks like this if you put it in a graph. So you have an increase in flow velocity on this axis, and you have the resuspension flux on that axis, and then below the critical flow velocity or shear stress, nothing will happen, and once it's above that, you will have a linear increase in resuspension flux, and then this resuspension constant is the regression coefficient of this line. Of course, this is theory in the sense it's only valid for a very uniform sediment which has only one grain size and one specific density and so on. Because otherwise you will have, this is more gradual probably, that some small particles will already resuspend, and at the end everything will resuspend, and then we'll have this straight line. You could actually measure this critical flow velocity which derives this shear stress. This is a picture of a machine that we made some years ago, and one of the master students also worked with that. He called it the hydrocopter, and which is actually two tubes that are with an inner tube and an outer tube, and there are blades here. They are turned in between these two tubes. So in the tube, inner and outer tube in this canal, there's a laminar flow made by this turning of the electromotor and these blades. And there's a light meter here to measure the light transparency. And I've seen it working a few times, and surprisingly, you increase the speed, and not so much things happen, but at a certain speed, it immediately, suddenly, completely gets dark. So this is, of course, the same goes, as I said before, that it will not be very gradually, but surprisingly, this is quite a fixed point. If you redo this a few times, you will see that every time at a certain speed, suddenly everything becomes resuspended and becomes like turbid. And we made a smaller one of this, and we did quite some experiments with that, because this critical flow velocity for resuspension is very important to know if you want to model, for instance, sediment transport and that sort of stuff. And here we did an experiment we have different types of vegetation that could control this resuspension flux, for instance, or different bacteria growing. And then this would typically be an outcome. Okay, I'll explain a little. We have a light beam here and a light cell. So we can measure the light passing this water column. And once it's clear, then you have a lot of light falling on the light meter. And once it's turbid, it decreases, of course. And then you have typically this type of responses. This is time. And the red line is a gradual increase in flow velocity. And the blue line is the transparency. And then you see it's not gradually, but also here you could say there's a certain point where there's a rapid decrease in transparency. So this is the point where there's a rapid resuspension. And then it's a bit arbitrary how to define the critical velocity. Is it here, or is it a bit here, or so that's always arbitrary. Question?
How do you know that's not the turbulence from the blades that's picking up the sediment? Because when one of the blades passes over, doesn't that give?
Yeah, but okay. So there's always quite a distance between the blades and the sediment, but the blades are moving the water. Yeah. So it's the same force. So the water is moving with the same speed as the blades, and they will take up the sediment to resuspend, as it was a river flowing. But if you do it like this, you could really gradually increase the speed to find this type of. We did a few of these experiments, and where we could find this critical flow velocity for resuspension, actually. And we did different types of sediment, for instance, with clay and peat and sand, and with some arrow bars. But we could expect, it makes sense that sand has a higher velocity where it starts resuspending, because usually it has more weight. And surprisingly, the peat, where you have a lot of organic material, that starts much earlier. This was let's say 9 centimeters per second flow velocity, that peat already starts to resuspend. So yeah, you see some differences here. And we also found a bit weak relation, but still it was significant. We found a relation of the organic matter content, so how much organic material we would have in the sediment, and the critical flow velocity. So if you have a higher organic matter content, it will earlier go into resuspension than if you have only a low percentage of organic matter. Then it takes already 20 centimeters per second to resuspend it. So the content, the type of sediment, they all contribute to different critical flow velocities. Okay, this is it takes time to explain, and I will make it not too long. And you can look, I will put this presentation on Blackboard, and you can have a look later if you want. So, this is more or less my last slide. So if we combine resuspension and settling, there's the two processes here. So the change in concentration of suspended solids is the settling flux, the resuspension flux, and the settling flux together. So it's the combination of the two. And one of the things you could do is that if you assume equilibrium state, so steady state at a certain moment, so you put it to 0 again, there's no change in concentration. So all these processes are in equilibrium. And you see that if you measure the suspended solid concentration at that point, it will be the ratio between the resuspension flux and the settling rate. Just putting this to 0 and rewriting this gives you this. And this is sometimes used to determine resuspension fluxes, because they are really difficult to determine. How do you do this? Because it's together with settling, and you cannot separate it like with sediment traps. It's difficult to measure resuspension fluxes. But if you measure the suspended solid concentrations for some time, and when it's sometimes steady, and you know how much is the settling rate, you can do an estimate of the resuspension flux. So therefore, it's used in this way. So now to the tutorials. Here it says Tuesday, but it might be that it's Wednesday. I'm not sure if Bart told you something about that. There would be perhaps a change in the lectures. But so there will be homework for you that you can hand in to us, and we will correct that, and we will give a mark for that, which contributes to your final mark and already gives you opportunity to practice with the exercises. And for the mark, you hand in 2 exercises, exercise 2 and on page 33 and exercise 3 on page 42. And I will put a form on Blackboard that you can use to fill it, but I always bring copies with in the tutorial. And you have time until this Friday to hand in, because next week we have other tutorials, and then we could already start marking during the weekend that you have your grades as soon as possible. So keep an eye on Blackboard. Hopefully it will be available soon for the lectures and the rooms.